Okay, thanks a lot. Okay, so for the most part, I want to sort of start over in this talk, but let me spend the first maybe 10 minutes just saying something about about this distance formula I ended with, and just give a little bit of explanation of maybe how that, a little bit of sort of hands-on feeling of what you can do with the distance formula and what it means, and sort of some way that it allows us to think about explicit paths in the mapping class group. And then I'll completely start over. And so if you were lost last time, hopefully this will help you. And if it doesn't, then you can still ignore that in about 10 minutes, and I'll start over afresh. So let me just remind you of this theorem. So this is the theorem of Minsky. So this is the distance theorem, the distance formula. It says the following. It says, so for any, I'm going to use slightly different notation, but for a reason. For any surface gamma, there exists, and any sufficiently large constant t, there exist constants. There exist k greater than or equal to 1, c greater than or equal to 0, such that for any pair of points, x and y, in the mapping class group of this surface, we have a way to estimate distance in the mapping class group. So I'll just say the distance between x and y, by which I mean the distance in the mapping class group, is kind of kc estimated by, so up to a bounded multiplicative error, the multiplicative constant's given by k and the additive constant by c. So is kc estimated by taking this infinite sum, where I sum over all gamma prime contained in gamma. And what do I do for each gamma prime, or contained in or equal to gamma, just to be explicit? I look at the distance in the curve complex of gamma prime, and I compare the projection to gamma prime of x and the projection to gamma prime, right? This really means the projection to the curve complex of gamma prime. Maybe I'll write that to be explicit, c of gamma prime of y. And then in order to actually make this give you a finite sum, we did this sort of double subscripts, which meant we ignored everything below this threshold. There's this threshold function, you throw away everything beneath that, and you sum it up, and then this kind of amazing theorem is that summing over these kind of, a priori infinite sum of distances in delta hyperbolic spaces actually is only finite, and so that you actually get a finite number there, and that finite number you get uniformly gives you an estimate for what the distance is in the mapping class group. Okay, so that's the theorem. So let me give a little explanation of something you can get out of that. I'll talk about some other applications of this later, but for now, let's think about the way the distance works. Let's pick some kind of explicit example, like the 5-hole sphere. So here's an example, like the 5-hole sphere. And suppose that we wanted to measure the distance between two mapping class groups. So between two mapping class elements. So remember, I said an element in the mapping class group, so an element in the mapping class group of S, or I guess I'm saying gamma now, right, corresponds to a marking, right, where a marking consisted of a Pants decomposition, and then some transverse data. And so the Pants decomposition, remember, was just a collection of simple closed curves, and then the transverse data was another set of simple closed curves. And so actually, for what I want to do today, I'm going to, for this simple example, we're going to just sort of ignore the transverse data. So let's just, for this simple example, let's ignore this transverse data. So for simplicity, in this example, let's ignore the transverse data. Okay, so if I wanted to pick some mapping class group element, it would just correspond to a Pants decomposition then. So a Pants decomposition would be some pair of curves which form a Pants decomposition. So each complementary component here is a 3-hole sphere. Okay, so it's just a pair of curves which are disjoint in S05 gives you a Pants decomposition. So let's think of that as our mapping class group element. So let's let X be this pair of curves, so this marking. So X is a marking. And then we want to take another point, so that's Y, so that's some other curve. So let's, you could draw some crazy curve here, which, let's see if I can even draw something that's, all right, let's go around one more. This will go around the back. All right, so maybe it worked, maybe it didn't, but nobody can see it because this room is so big. So anyway, suppose that was a simple closed curve, and then I take some other simple closed curve disjoint from that, and so Y is also some other pair of curves which I drew, which is some other marking. Okay, and so now what I'd like to do is find, I want to compute the distance between them, and so maybe what I'd like to do is find a path connecting X to Y. All right, so here's what I'm going to do. So an observation is, well, our marking, right, since we're ignoring the transverse data, is just the Pants decomposition. A Pants decomposition is a pair of disjoint curves. So that's just a simplex in the curve complex of S05. So X and Y each correspond to simplices in the curve complex of S05. Okay, so let's draw a picture. Here's so X is this pair of curves, which maybe I'll call X1 and X2. And then over here, I've got Y1 and Y2, and these are connected by an edge, and these are connected by an edge. And this whole picture I'm drawing here is sitting inside the curve complex of S05. Okay? So how could I try to build, what I want to build is, this is like a mapping class element, and this is a mapping class. So I want to find a sequence of mapping class elements that connect them together. So here's something you could do. I could pick an arbitrary element of X, maybe X1, and an arbitrary element of Y, maybe Y1, and I could connect them by a geodesic. So this is let's say this is gamma 0, which is X1, gamma 1, gamma 2, all the way to gamma n, which is Y1. And so this set of gamma i's is a geodesic in S05. Okay? Pick some geodesic. This is a geodesic metric space in the curve complex. Right, sorry, in C of S05. Thank you very much. Okay, so then here's my geodesic. All right, well, how could I build a sequence of paths? Well, one thing I could do is notice that, right, so since both gamma 1 and gamma 2 are disjoint from X1, they both, right, so let's just draw this, maybe I should start over here. Let's start with Y1 and Y2 because those were easier to draw. Okay, so my Y1 was this curve here. Which one was it? I had this curve here. This is, I switched colors. Okay, fine. Let's just switch colors so that we're consistent. The red one, doesn't matter what I call it, but let's start here. This is a better numbering scheme. There's X1 and X2, and here is, doesn't matter, Y1 and Y2. Okay, great. All right, good, that works out better anyways. Okay, so here's my curve X1. Okay, and then we have X2 is somewhere here, which we've drawn already. Here's X2. I don't know exactly where gamma 1 is, but I do know that it's disjoint from gamma 0. Okay, so gamma 1 is some curve. Oh yeah. Okay. Anyways, it's some curve over here, which is simple and is disjoint from x1. So both gamma 1 and x2 are in the curve complex of S04. Because if both of them avoid x1, so they're both disjoint from this curve, so they can't cross over to this side at all, so they both live inside this 4-hole sphere. Okay, well that's kind of nice because now I have 2 points in the 4-hole sphere. I know that the curve complex of the 4-hole sphere, I know that in the curve complex of the 4-hole sphere, there's a geodesic there. So what I can actually do is, so this is a general property, right? That if you take a curve and you remove it, then its complement is some collection of subsurfaces, and in the curve complex of whatever surface you're in, the link of that corresponds to curve complexes of the complementary components. Okay, so these things, right? These live in, well, they're both in the curve complex of S05, but actually they're also in some slice of the curve complex of the 4-hole sphere. Okay, so what that means is then I could pick some geodesic here. So this is a geodesic in the curve complex of, let's explicitly say, of I'll say S04, right, which is explicitly the curve complex of my S05 minus gamma 0. Right, that's the particular S04 that it is. That's 2 components. It's one component of that object. So I can build this sequence here. Now, really, each one of these vertices, right, they're all disjoint from x1. So I could think of this sequence of mapping class elements, right? I've got this sequence of Pancy compositions starting with x1, x2 as a pair, and ending with x1, gamma 1 as a pair. Okay, and then you could repeat, right? So x1 and gamma 2 are both disjoint from x1. So you repeat this process again. Okay, so now x1 and gamma 2 are both in C of S minus S05 minus gamma 1, right, which is just a copy of C of S04. Okay, and so I connected those by some sequence of geodesics. And then you repeat. Okay, and you keep doing this. And you get this path that sort of wanders through the space. You get this sequence of pairs of Pancy compositions. Now, those pairs of Pancy compositions then, it turns out, are each sort of distance one from the next in the mapping class group. Okay, so this thing that we get then, maybe I'll draw it in green, kind of following this sequence of Pancy compositions, gives me a path in the mapping class group. So this is a path in the mapping class group of S05 connecting X and Y. Okay, so this is a path connecting X and Y. And what do we know about this path? Well, one thing we know, right, it looks like it's an extremely inefficient path from the way I've drawn it, but what do we know about this? We know that, for instance, when I marched from x1, x2 to x1, gamma 1, it turns out that somehow there's some distance term here inside the curve complex of this particular subsurface. And that there's some term then that shows up in the distance formula over here. And so each one of these little segments corresponds to some term in the distance formula. And so this is some path which then gives you an upper bound for the distance between x and y. But the Masur-Minsky distance formula then tells us that even though, as I've drawn it, that path looks very inefficient, that path is a quasi-geodesic in the mapping class group. So you build paths in the mapping class group out of these paths in the curve complex. And we kind of did this by ignoring the transverse data, but it turns out that the same picture works on any surface, and including the transverse data. You just get things that are more complicated, where if I wanted to move from here to here, you end up getting kind of nested loops, nested versions, where these things can be very complicated in here, and that corresponds to kind of passing through different subsurfaces. So I won't go into detail about that now, but this is sort of the general picture of the way that paths can be of the way that efficient family of paths, a family of quasi-geodesics, can be constructed in the mapping class group. Okay, so all right, so that was kind of the closure of what I wanted to finish last time. Yeah, that's right. Yeah. So they call these hierarchy paths, and in fact, right, that name of hierarchy path is what motivated kind of our definition of hierarchy hyperbolic spaces, because we want to kind of generate a similar sort of structure. Okay, so having said that, now I'm gonna come back to this, but roughly I'm gonna sort of start over again. So this is really where talk 2 is gonna start, and so I'll call this, right, this is maybe talk 2. This is curve complexes. Right, we've been talking about curve complexes, but for the mapping class group, these are going to be curve complexes for cube complexes. Okay, so what I want to do is we're going to build sort of an analogous theory to what works in the mapping class group for cube complexes. So the goal is to build machinery similar to the C of S machinery, the C of S tools in the mapping class group for cube complexes. Okay, so this was sort of our motivating example in developing a theory of hierarchy hyperbolic spaces. So I'm going to go through this specific example in some detail today, and then tomorrow or next Wednesday or whatever, when I talk, right, the next talk in the series, I'll sort of put this all together, and I'll explain how there's some, a single unifying language that will describe, everything at once and allow you to prove a bunch of theorems. But for now, I want to kind of focus on this concrete example. Yeah, so I'm going to just say cube complexes most of the time, but always it means cat 0 cube complexes. Yeah, thanks. Okay, so let me start by defining, and actually let me say that actually everything I'm going to say now is going to be, so this is all joint work with Mark Hagen and Alessandro Sisto. Okay. Right. Okay. So we've been hearing in Mika's talk quite a bit about cube complexes. So what I want to do is start by talking about sort of a particular family of cube complexes and sort of focus on that family, the right-angled Artin groups, and the cube complexes associated to them, and then I'll kind of say things in a general language that will work. Most of them will work for in the general case also, but sort of dealing with this particular example will give us something concrete to work with. Okay, I meant to ask before the talk. So I only saw one of your 3 talks where you did not mention rags. Did you talk about rags? Who knows what a rag is? Great, I'll define what a rag is then. So what I want to talk about is right-angled Artin groups. So given a simplicial graph gamma, okay, then the right-angled Artin group Artin group, abbreviated by RAG, right-angled Artin group associated to gamma is the group with the following presentation, is the following group. Okay, so here's the explicit presentation. So the generators, so here's the presentation. Generators are in bijective correspondence with vertices of gamma. Okay, and the defining relators so you do a commutation relation, right? Just A, B, A inverse, B inverse for each AB in, for each AB in the edges of gamma. Okay, so if you have an edge, you say those two generators commute. Otherwise, you don't do anything with that. So here's some concrete examples, right? The simplest possible example is n vertices and no edges gives us what group? Good, free group, right? So the free group on n generators. N generators, okay? And so maybe that's, example one. Example two is, right, the simplex, the n-dimensional, so the simplex with n vertices. Right, that gives us, right, every pair of generators commute, so we just get the free abelian group of rank n, okay? So the free abelian group. Okay, so this family of groups interpolates between these two extremes. And so just to put one more kind of non-trivial example down, so here's a path of length 3. Okay, so it turns out this is a group that's been well studied. So this actually even has a name. This is called the Croke-Kleiner example. So this is called the Croke-Kleiner example. And it turns out that this is pi1 of a 3-manifold. Okay, so it's not obvious from this sort of simple presentation that you could get fundamental groups of 3-manifolds, but it turns out that you can. Actually, it turns out that the 3-manifolds correspond to right-angled Artin groups whose presentation graph is a tree, but then you can also get other interesting 3-manifolds. You can also get other interesting groups. So maybe just to draw one more, right? Mladen's favorite one, or at least for a while, was the pentagon group. So this is an interesting one. It's got finite outer automorphism group and a bunch of other interesting properties related to quasi-symmetric rigidity. So these are kind of the basic examples. These are a few basic examples to get you started. Okay, so these are the groups. It's funny, it's disconcerting when it cuts out when you're in the audience, but it's even more when you're giving the lecture. Right, so the next thing I want to define is that to any one of these rags, there's a canonical association. So actually, let me introduce a name. So I'm going to call this, actually, let's just call this A sub gamma. Right, so that's the name of the group. So to each A gamma, we can associate a cat0 cube complex. Okay, so there's a cat0 cube complex, which is the universal cover of a, well, right, this is a k pi 1, and the universal cover is this cat0 cube complex. So the cube complex called the Salvetti complex. Okay, so how do we define the Salvetti complex? We just take a loop. So add a loop. So take a loop for each generator. So take a wedge of n circles if there are n vertices. One for each generator. Okay, so you start with this wedge, and then what do? I glue in the obvious things, right? So I glue in a square. So glue in a square for each commutation relation, right? For each edge in the graph gamma, and more generally, and an n cube for each n simplex, and maybe that's n minus 1 or n plus 1. Does that work? Right, for each, yes, those numbers match up. Anyways, right, so if you have a triangle, oh, I see, so there should be an n plus 1. So if you have a triangle, right, so if you have 3 generators that commute, then that corresponds to a cube that you want to put in. So whatever that means. So this has dimension 2, so an n plus 1 cube for each n simplex. Okay, so you just kind of keep booleaning these things in. So that gives you the Salvetti complex, and we'll be interested in, actually this, I'm lying slightly, so there's associated a cube complex, period. I should say this. The Salvetti complex is this, the universal cover of the Salvetti complex is a cat zero cube complex, which I'm going to denote CCC, and we'll denote, which we denote just by, I'll just call it maybe S sub gamma. Okay, so S sub gamma will be the universal cover of this cube. There's this cube complex that has the fundamental group A sub gamma. The universal cover of that is a cat zero cube complex, and I'll call that S sub gamma. Okay. Anything else? Okay, and so what we're going to do now is we want to study the large scale geometry of cat zero cube, of Riding-Lauderdale groups, and more generally of cat zero cube complexes by something that's analogous to the curve complex of a surface. So that's what I'm going to define now. Yeah. I start with the Subhojoy graph. So A sub gamma is the Riding-Lauderdale group associated to that. Oh, so right. So this complex I build, the fundamental group of it is A sub gamma. And this is just the universe, this S sub gamma is just the universal cover of that complex. I know I wanted to leave that up because I'm going to come back to it, but I see I could even go to the left of that. I'm really, okay, so maybe I'll do that. Okay, I'll go over there. So let's start with the, right, so here's the definition. Let's let X be a cat zero cube complex. Okay, so we define, so the contact graph associated to X, the contact graph of my curly X, which is, so in this kind of suggestive way, I'm going to call this C of X, okay? And I'm going to tell you exactly what it's built from, consists of, okay? So the vertices, so I'm going to put one vertex for every hyperplane of that cat zero cube complex. So vertices correspond to hyperplanes in X. Okay, vertices correspond to hyperplanes. And what are the edges? So it turns out that the right version of the right analog of the curve complex of the mapping class group is to build edges corresponding to pairs of hyperplanes, which can't be separated by a third, which cannot be separated. They don't have to be disjoint. Yeah, they don't have to be disjoint. Pairs of hyperplanes which cannot be separated by a third. So they either intersect. So let's see. Maybe I'll say here equivalently. their hyperplane carriers intersect. Okay, so maybe they actually intersect on the nose, in which case then you put an edge. Maybe they don't intersect, and I'll draw some pictures in a minute. Maybe they don't intersect, but their carriers intersect. Okay, so the carriers are, you just take the union of all the cubes that contain that hyperplane. That's the hyperplane carrier, and if those intersect, then you also put an edge. Okay, so that's the complex. Okay, I'm going to skip this board for now. Right, so let me do a few concrete examples. So maybe the simplest example is the curve complex of the real line with the standard cubulation. So R with the standard cubulation. Okay, so just take the integers and take the intervals between them. Okay, so what's its contact graph going to look like? Well, what are the hyperplanes here? Right, so the hyperplanes correspond to midpoints of edges. Okay, so hyperplanes are, in this example, are midpoints of edges. Okay, so here's three things. And now, when do those carry? And then the carrier will be the entire interval containing it. So when do those intersect? Well, they intersect exactly the adjacent one. Okay, so we've got infinitely many hyperplanes, and each one has a carrier which intersects the one before it and the one after it. So the contact graph associated to this is isomorphic to R with the standard cubulation. Okay, it's the same thing. Okay, so that's maybe the simplest example. So here's a slightly more interesting example. Let's take the contact graph of R cross R. Okay, so let's draw a picture. Okay, so here the hyperplanes are these vertical and horizontal lines. Maybe I'll draw these vertical lines in red and the horizontal lines, the vertical lines in blue and the horizontal lines in red. Okay, so we know that the blue ones give us this copy of R, and the red ones also, right, these red hyperplanes give us a copy of R. And there's some more edges, right? Every red hyperplane intersects every blue hyperplane. Okay, so what I do is I take the join of these two graphs. Okay, and this goes in both directions. So this contact graph is isomorphic to what I'll call R star R. This is the join of these two graphs. Okay, connect every vertex in one to every vertex in the other. And more generally, right, this was a totally general construction, so more generally, the contact graph of X cross Y is isomorphic to the contact graph of X cross the contact graph of Y. Okay, so actually one thing to note, right, this was infinite diameter, this now has diameter 2. Okay, and maybe just one more example is let me just do a finite example, right? So there's nothing I said here that required that these be infinite curve complexes, that these be infinite cube complexes that I'm working with. So we could even take the contact graph of some concrete examples. So let's see, I drew one. I could do something slightly nice. So let's do this. Okay, so here's some simple cube complex. Okay, so you could draw the hyperplanes here. Right, there's 1, 2, 3, 4, 5, 6 hyperplanes, and then you could start to look at their intersection patterns. So there will be 4, 5, 6, and then let's see if I wanted to label these. What did I do? D, E, F, A, B, C. Okay, so actually it turns out that that most of these things intersect, but some of them don't. So let me just draw. I won't fill out this completely, but for instance, E intersects B, intersects C. Okay, the carrier of B intersects the carrier of D and the carrier of E, and actually this cube overlaps with this cube, so it even so everything intersects E. So E, wherever it is connected to everything. Maybe this is E, and that connects to everything. Whereas, right, if I took D, maybe this is D here, right, the carrier of D will be this square. Well, that's going to intersect, it's going to intersect the carrier of A, and it's going to intersect the carrier of E, but it doesn't intersect the carrier of F, and it doesn't intersect the carrier of C, but it does intersect the carrier of B. Does that make sense? So that's sort of, so I won't draw the whole thing, but there's more edges to put in here. So here's an exercise, fill this in. Okay, so figure out exactly which are there, and it's almost all the edges. There's maybe 2 or 3 or 4 that are missing. I forgot. Yeah. Yeah, they intersect at one point, but that's still a non-trivial intersection. So E and B are connected. D and B, they don't intersect. Their carriers. Sorry. E and B do intersect. Sorry, you're right. Yes, thank you. Yeah, they do intersect. D doesn't intersect the carrier of F, and it doesn't intersect the carrier of C. Thank you. So D is connected to everything except for C and F. Yeah. Good. So people understand this. Great. So these are contact graphs. Okay, so here's a theorem of Mark Hagen's. So he was interested in these in his thesis, and he proved that for any cat-0 cube complex that you give, actually, right. So for any x, so which means cat-0 cube complex, the contact graph is a quasi-tree. In fact, it's a uniform quality quasi-tree. So is uniformly quasi-isometric to a simplicial tree. With actually reasonably small constants. I think it's like 10-10 quasi-isometric or something like that. Okay, so these are not just hyperbolic, right? The curve graphs were all hyperbolic when we talked about them for the mapping class group. The contact graphs not only are hyperbolic, but they're actually quasi-trees. Okay, so this tree, I didn't say infinite tree. So uniform means right. The constants don't depend on. So it's like I think 10-10 is right. Uniform over all cat-0 spaces. Yeah. Okay, so I was more clever in my notes than I was on the board. So it turns out that so these are the contact graphs, and these are useful for studying the geometry of cat-0 cube complexes, but they're actually we're actually going to want to refine a slight refinement of this definition. So let me mention one more thing about these, and then I'll explain how we can then refine these, and hopefully update my notation at the same time. So for any convex subset H contained in a cat-0 cube complex X, just like we defined the contact graph for X, we could define the contact graph for that convex subset. Okay, so we can define the contact graph of H. Okay, because it just you just look at all the hyperplanes in X which intersect H, and then you put a vertex for each one of those, and again the edges correspond to intersections of hyperplane carriers, and it turns out that because of convexity, whatever intersections you had inside the whole cat-zero cube complex, you get inside that convex subset. So we can define this not just for our original cat-zero cube complex, but for any convex subset. And let's note that the contact graph of H is contained in the contact graph that you started with. Okay, so something that we can then do if we start with a convex subset, right? So if you have a convex subset, there's a nice projection map from the ambient space to that convex subset. So just closest point projection. So for any, right, so since H is convex, there exists a closest point projection map projection from X to H. All right, so given that, so then we define, so what we're going to do is we're going to define pi sub H, okay, which maps our original space to the contact graph of H. And we're going to do that just by taking any point. Okay, you take your arbitrary point, you look at the right, if your point is you look at your point, and then you take your point, and then you look at if you need to closest point projection to H, and then you take the union, so the union of all the hyperplanes containing hyperplanes, in H containing X. Okay, so you have some cat-zero cube complex X, you have some convex subset H. You can take your point, you can look at closest point inside H, and then you look at all the hyperplanes inside H which contain it. So all the hyperplanes in H which contain it, right, they all must intersect non-trivially because they all contain X. So actually this sends points, so this map sends points to simplices in C of H. So when we define the projection from the mapping class group to the curve complex of a subsurface, we were sending points to bounded diameter sets. Here, not only are they bounded diameter sets, but there's something even nicer. They're diameter 1 sets. They're simplices inside the contact graph. There's no hyperplanes passing through X. It's a cube complex. Every point is on some. Right. So yeah. So I should say, right, hyperplane carriers is what I should be thinking about here. Yes, hyperplanes which intersect. Yeah. So right. So yeah. What I should say is closest point project X to H, and then you look at all the hyperplanes. Yeah. Sorry. Through the projected X. Yes. 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 Yeah. Okay. So this sends points to bounded diameter sets. So. Right. So now what we need to do is. So for many purposes, this graph is enough. For our purposes, actually, we need to modify this slightly. So I'm going to explain kind of the general cat-zero cube complex version, and then say what it is specifically for right-angled Artin groups afterwards. So here's the general statement. So the factored contact graph of X is, so I'll denote this C hat. I'm going to denote it C hat here, and then afterwards we're going to ignore the other one and we'll just mean this one. So it's defined to be the following thing. You take your original contact graph, and then I want to, right, as you can guess from the notation, we want to build something similar to what we got in the Masur-Minsky distance formula. And so as we've defined it, we might be overcounting things significantly. So what we're going to do is we want all the distance in a contact graph of a subgroup to kind of uniquely contain that information. So we're going to cone off information that exists in smaller subgraphs. So what I'm going to do is I'm going to take C of X and I'm going to add some vertices and some edges. So the vertices I'm going to add are, I'm going to add a vertex for every hyperplane in X. So I'm going to add a vertex V sub H for each hyperplane H contained in X. And then I'm going to add some edges. What are the edges going to be? I'm going to add an edge from V sub H to V for each V in the contact graph, right? The contact graph that I started with of H. So I'm going to look at every possible hyperplane. For every hyperplane, I'm going to add a new vertex, and then I'm going to kind of cone off the contact graph associated to the contact graph from that hyperplane, the sort of sub-contact graph. So what I want is I take the hyperplane carrier. Yeah. So right. So I'm abusing notation here. So I'm going back and forth between the hyperplane and the hyperplane carrier. The hyperplane carrier is a convex cat-zero cube complex sitting inside your original space, and that's what I'm taking. So right, I'm abusing this notation slightly. So I'm abusing the notation by I'm saying it's the curve complex of the hyperplane, but it's really the curve complex associated with the hyperplane carrier. Oh, what are the edges here? The edges are, I put in these new vertices. Any one of the new vertices corresponds to a particular hyperplane. So I take that hyperplane. So the edges in that, so you also had in that hyperplane, there's lots of in that hyperplane H, there may be lots of other hyperplanes. Each one of those other hyperplanes is a vertex in C sub H thought of as a subset of C of X. Okay, so in C of X, which is here, I'm now coning all those off. Okay, so I had my original thing, and then I've kind of coned off a bunch of stuff along the way. Okay, I need this to stop dinging. Okay, so let me say what this is in the right-angled Artin group case. So note for S sub gamma. Okay, in the Salvetti, if you think about the Salvetti complex of the writing associated to gamma, then up to quasi-isometry, you can get the exact same thing in the following way. So for S sub gamma up to quasi-isometry, so the contact graph of S sub gamma is equal to, start with the Cayley graph of your right-angled Artin group, and then I'm going to cone off certain things in that Artin group, which are take this and then cone off. So let me say this: start with A sub gamma and cone off A sub delta for each, well, actually, let me say G times A sub delta for each delta contained in gamma, properly contained in gamma, and each G in A of gamma. Okay, so inside the Cayley graph of A sub gamma, you've got a bunch of, right, so we have this graph. Right, here's my right angled arc group. Inside this, I've got a bunch of subgraphs. Okay, inside the Cayley graph, I can think about the subgroups corresponding to subgraphs. Okay, those turn out to be isometrically embedded, so those are giving you convex subcomplexes inside the cat-zero cube complex. So you look at one for every subgraph, and then I cone those off. So I cone off every subgraph and every left coset of one of those subgraphs inside my original right-angled arc group. So that up to quasi-isometry is just another way of thinking about the factored contact graph. So there's sort of a very concrete, simple construction in this case. Okay. So now what can we do with this factored contact graph? So actually, let me put one theorem about it up here. So here's the theorem. Oh, sorry, I should have put a hat here. Right. Yes. Yeah. Okay, so a theorem is that these factored contact graphs, S sub gamma, well, sorry, this works in general. For any cat-zero cube complex, this is uniformly Qi to a tree. So is uniformly, well, yeah, is uniform, we don't care about the uniformity here, but is uniformly quasi-isometric to a simplicial tree. With slightly worse constants, but still kind of fairly small constants. Okay, so great. So now we've built, so these are now our analogs of the curve complex. So what can we say about these? So now I'm at the perfect spot because I've written this theorem right here, okay? So it turns out that this theorem of Masur-Minsky can be modified. So with Hagen and Sisto, oh, maybe is the green not visible? I forget which color is not visible. This looks bright. And now it's green and orange. That's great, right? So the right colors. Okay. So for any, instead of surface, let me say graph, gamma, and for any sufficiently large t, there's constants, so that for any pair of points inside the right angled arc group of gamma, we have that you can estimate, so I didn't bother to write the distance here, right? This was before distance in the mapping class group, now it's distance in the right angled arc group. This distance is uniformly estimated by looking over all, you look over all subgraphs, and you look over all subgraphs, and you sum over, actually, I need to look over all subgraphs and potentially left cosets of them, and then I sum up these distances that I get inside the contact graph of that arc group of a subgraph. Okay, so for every graph, you look at every possible subgraph. Inside those subgraphs, you get a bunch of different quasi-trees, and I just sum over these projections from my original space to these quasi-trees, and I can recover distance inside the arc group that I wanted. So each one of these, once I've done this, right, these tend to all be infinite diameter. What this coning off ensured was, it ensures that inside every subgraph, I'm capturing distance inside that subgraph, but that doesn't occur inside a subgraph inside that. So you sort of get exactly the distance that occurs sort of at that top level, whatever that means, right? So somehow, right, the distance has to do with the way that you travel through hyperplanes, and you want to cone off, if the hyperplanes occurred in something smaller, you don't want to overcount them. Otherwise, there's no way you'd be able to get some uniform bounds. So you cone off things so that you're not double counting at these low levels, and with that coning, then you get, so I guess I should say here, right, these are my Right. In my original, in the notation of my notes where I was clever, I had the primes before and I got rid of the primes here. But I said that I didn't write it. So what I want is, right, these are subgraphs, and then there should be also G and A sub gamma, and then, right, if I'm writing this carefully, then these are left cosets, and then once I've done that, if I'm being careful, then there's a caveat, which is I was trying to avoid saying, but now you're forcing me to say it. So this is up to parallelism. Parallel. Okay, so if I have two different left cosets and they cross the same family of hyperplanes, that's what I think of as being parallel, then I don't want to double count them. I count once for every parallelism class. Okay, which form? This pi sub c hat of gamma prime. So I want to measure distance. I want to measure distance here. The projection that I said over there. So you take the closest. You have the whole right angled arc group gamma. You have the right angled arc group A sub gamma. You project. You take the closest point projection to this particular coset, and then you take the nearest point projection, but that brings you into the coset, and then you take all the hyperplanes inside that coset that contain this, and that gives you an element of c hat of. That gives you an element of c hat. Well, it gives you an element of c of this particular coset, and then that then gives you an element of c hat of that particular coset. It's pi sub h, but my h is now g of gamma, or g of gamma prime, or whatever I called it. That's right. So it's actually right. So it's c of it's projection to c, but then c hat lives inside. So I project into this. That gives me a point in here, which is a particular point in here. Okay. So we recover a distance formula, and in that distance formula, so we can do. Just keep warming. Okay. In that distance formula, we can do things similar to what we did in the mapping class group. So remember, in the mapping class group setting, you were summing over all these subsurfaces, and then we got different behavior depending on how those subsurfaces related to each other. So it turns out that in this general setting, you can do something similar. So in the mapping class group of S, there is a trichotomy okay, which is the following. So we mentioned this before. There's a trichotomy where if I'll call it this, if gamma prime, gamma double prime are both subsurfaces inside gamma, so these are subsurfaces, okay, then either, there's three cases. So either gamma 1 intersect gamma 2, so let's just write like this, gamma 1 and gamma 2, or gamma prime are just, gamma prime and gamma double prime are disjoint. Okay, and in that case, I mentioned this last time, in that case, this implied that when I looked at the projection to gamma prime cross the projection to gamma double prime, the image of that was roughly onto C of gamma prime cross C of gamma double prime. Okay, so if you had disjoint subsurfaces, then these projection maps were roughly onto this product. And then there were two other cases. So the case that got discussed, so the case that didn't get discussed much was gamma prime. Well, I'll say the case that was discussed. So if gamma prime intersects gamma double prime non-trivially, and they're non-nested, well, let's just say this. I'll say this, and they're non-nested. Okay, then that's where you got Mladen's SP1, or it's not SP1, P1, right? The weak Behrstock inequality. So, so the image, right? The image of this projection looked like, right? It was coarsely this wedge of two spaces. Okay, so it's coarsely a wedge. So it's coarsely C of gamma prime, wedge, C of gamma double prime. Okay, and then there's one more case, which is if gamma prime is contained in gamma double prime, or vice versa. So we didn't discuss that much, but it turns out that that also has a very similar picture. It also corresponds roughly to a wedge. Okay, so that was in the mapping class group. It turns out that in the case of a cat zero cube complex, you get a similar kind of trichotomy. So, so the case of disjointness. So in the maybe I should do this in orange. So in a RAG, actually maybe let's write it over here. So in a right angled Artin group, if you have two different convex subsets, right? These correspond to like left cosets of some right angled subgroup. Then the analog of being disjoint, right? So in X, the analog is spanning a direct product. Okay, and for Misha, it's spanning a direct product up to parallelism, but for everybody else that doesn't want to think about that, it's just like whether or not they span a direct product. So if I look inside, if I have a right angled Artin group like this one, and I look at this vertex and this vertex, they're sitting inside an edge, so they span a direct product. They span a z squared inside this right angled Artin group. So I would think of those two. I would think of the two subcomplexes. I would think of those two cosets as being in this category, and we call that being orthogonal. So we call this being orthogonal. And if you're orthogonal, then these projections are coarsely onto. Okay, so then there's nesting. Well, non-nesting in the case of the mapping class group correspond to subsurface nesting, but you can also have as complexes inside X. You can think about those complexes and whether they nest inside each other. So nesting. Actually, maybe that's this third column, right? This in general is just nesting as subcomplexes. Okay, and in the nesting as subcomplex case, we get there's an explicit picture like this that controls what their geometry is. And in this third case, which we call being transverse, right? So these are nesting, and in the transverse case, you get the same sort of implication where you understand. You also satisfy exactly this inequality that leads to this image being a cross like this. Okay, so if we want to understand this distance formula this distance formula can be understood using the exact same kind of general scheme that it could be in the mapping class group setting. You also get the same sort of trichotomy, and then the same kind of development of how those projections work. Okay, so let me give a couple useful properties that we get from that. So these restrictions, right? So if we think about, just like for the mapping class group, you could think of this map that sends X. You could think of roughly this map which sends X into this product overall, let's say lambda contained inside gamma, and maybe all G in A sub gamma. You can look at the product of these curve complexes of G of A sub lambda. Okay, so you map into this product of all these curve complexes, just like with the mapping class group. And in this, right, we don't quite have a distance formula. We have this same sort of quasi-distance formula, and we know when you map to pairs of projections, we know how these look. Okay, so you can think of this you can think of this as saying, given a point in a mapping class group, I can associate that to that an infinite vector, right? I can associate to that where its projections are in every one of these coordinates. And we think of these conditions are the consistency conditions. So in order to given one of these vectors, if we hoped that it came from a cat zero cube complex, it would have to satisfy. Well, this doesn't give you any restriction, but these two both give you restrictions. Okay, so those are these together are the consistency conditions. Actually, I should say that our proof of the distance formula in the cat zero cube complex case. Well, we actually have two proofs, but one of the proofs generalizes and gives a new proof in the mapping class group case as well. So we have a theorem which is also that there's these consistency conditions. So given a vector in this product of curve complexes or C hats of G, A, lambdas, okay, you can ask when that comes from some element in the cube complex, when that comes from some element in the right-angled Artin group. And our theorem is that given a vector in this, it comes from, or it is, I'll just say, right, we can make this precise if someone wants, but it comes from an element of X, if and only if up to bounded air, so this if and only if is up to bounded air, it satisfies the consistency conditions. Okay, so what that means is that it turns out that not only can you go from the curve from the right-angled Artin group to project all these things, but if you give me a bunch of elements inside all these contact graphs, you can. It turns out that as long as locally, right, as long as pairwise they satisfy these necessary set of conditions, then you can find some element inside the original cat zero cube complex, which projects to all those coordinates kind of uniformly close coordinate-wise. Okay, so this has an analog. This was motivated by a theorem in the mapping class group, which I proved with Bruce Kleiner and Yair Minsky and Lee Mosier. So it's not, again, because of this fact that there's this sort of thresholding. So it's not the L1 metric on that product. On the other hand, right, you can use these projection complexes and get something. You can build a complex where you don't need to use an L1 metric. Okay, so I've got 10 more minutes or 5 more minutes. So let me give one more application, and then next time what I want to do is build up. I'll kind of explain a uniform framework that covers that covers the Artin group case and the mapping class group case and a number of other cases, and I'll give some more applications. But let me just say one more for now. Something that Mladen mentioned briefly was acylindricity. Okay, so what was the definition of an acylindrical action? So an acylindrical action. Oh, there's a timer there. I can't believe I wait. Okay, now I know that for next time. That's useful. Okay, so what does acylindricity mean? So a group acts acylindrically on a space if it has the property that for any pair of points, if you pick any pair of points that are far enough away, and you want to know how many elements kind of coarsely stabilize those points. So it doesn't move x very far and it doesn't move y very far. Right? So how many elements don't move this very far while simultaneously not moving this very far? Then the cardinality of that is bounded. Okay, so acylindricity means that the cardinality of the coarse stabilizers of distant points is uniformly bounded. Okay, so I'm going to give kind of a pair of related theorems about cat zero cube complexes, or about groups acting co-compactly on cat zero cube complexes. I guess actually one thing I should say is I've been mostly talking about writing Laurent groups. I've been saying the same thing works for cat zero cube complexes. To prove it for cat zero cube complexes, Sisto and Hagen and I had proved that for a class of cat zero cube complexes, the special cube complexes, and then Hagen and Tim Seuss generalized that to work for all cat zero cube complexes. So yeah, the general extension to co-compactly cubulated groups requires that. Okay, so what's the theorem? So here's the theorem. So the first one, I'll put it in two parts. The first one is with Hagen and Sisto. So we proved that given any group G acting geometrically, so properly discontinuously and co-compactly, geometrically, on a cat zero cube complex X, then G acts acylindrically on C hat of X. And moreover, right, so sometimes this may be bounded diameter, and so I'll just say, so parenthetically, and C hat of X is finite diameter if and only if G is a direct product. Okay, so if G is not a direct product, then this group is what's called acylindrically hyperbolic. It acts non-trivially. Every group acts acylindrically on a point, and so, but it's interesting when the hyperbolic space is infinite diameter, and this says that you do get an infinite diameter space as long as G is not a direct product. As long as, yeah, sorry, thank you. Yeah, X. Thank you. Okay, so that's part one. Part two, which is joint with Carolyn Abbott and Matt Durham, is a strengthening of this, which says, in the case where C hat of X is infinite diameter, so when C hat of X is infinite diameter, then not only does it act acylindrically on this space, but then there exists a infinite diameter hyperbolic space Z, on which G acts acylindrically and such that every element in G which acts acylindrically on some hyperbolic space, which acts loxodromically on some hyperbolic space, acts loxodromically in this particular action. Okay, so then there exists a hyperbolic space on which G acts acylindrically, and such that any element of G which can act loxodromically on a hyperbolic space can act loxodromically on a hyperbolic space does. Okay, so this is called a universal acylindrical action. So any element, these may be different spaces on which these different elements act loxodromically, but we built some hyperbolic space where simultaneously any element that did act loxodromically in some acylindrical action acts acts loxodromically in this particular one. So this is what's called a universal acylindrical action. And maybe there's a place to stop. Well, so these satisfy the axioms, right? The projection complex axioms had to do with having the bounded projection, and that was the fact that these images were always oblique, and they satisfy, right, so you can find kind of sub collections of these where you satisfy this, wherever my transversality one is. You can find kind of these sub collections, just like if you take a bunch of subsurfaces which pairwise all overlap each other, then you get the axioms for projection complex. Similarly, you can build kind of subcomplexes in these that all satisfy the axioms for projection complex. Right. It's the ones that satisfy this axiom.
The whole hierarchy machinery can be recovered from this. I mean, you can have a combing using hierarchy paths, as in the mapping class group.
So a combing. So yeah, we can build combings on all these spaces.
No, using sort of a
So something I didn't say was right. So I constructed explicitly this sort of family of paths in the mapping class group, and I explained what those were. It turns out that same machinery allows us to construct a family of paths inside a writing Laurent group, but that's already known. But more generally, inside any of these family of class spaces that I'll talk about next time, the hierarchy hyperbolic spaces. So these are there's some set of axioms which I won't sort of itemize, but these things these play a large role in what those axioms are, and any one of those satisfies this sort of general situation that we'll sort of outline next time and we'll build some analogs of what Misha was talking about with understanding kind of generalizations of the Morse lemma. We'll kind of prove a version of that for higher dimensional quasi-flats to classify images of quasi-flats, and we'll do some other stuff next time too. He's been trying to ask one. Okay.
Right. So for anything that satisfies the consistency conditions, then you can lift it up either to a mapping class or to an element up in the
right.
So for things that don't satisfy the consistency conditions, is there any way to assign meaning in the original group?
No. I mean, right. The theorem says that. That's exactly what the theorem says. Is inside this infinite product, you might want to know what things have anything to do with the mapping class group, and it's exactly or a cat-zero cube complex is exactly the ones that come from the consistency conditions. If you don't satisfy those, there's no way to there's no way to synchronize them. You won't be able to get from the projection complex point of view. Kind of they don't match up. They don't match up in the right way. I mean, they don't. In this sort of point of view, they don't. You don't have if the image doesn't lie inside this, then you're not going to be able. Then it just doesn't geometrically doesn't look right. So.
So you can't get a single element back upstairs, but could you get like some kind of collection or?
So yeah, I mean, so in principle, you could have it on some you might be able to you might know something about, right? So something I didn't talk about, but maybe I will a little bit next time, is that inside, for instance, inside a mapping class group or inside a cat-zero cube complex, you could look at some subgraph gamma prime, and then you could look inside that gamma prime, you could look at all the things nested inside that, right? That'll be like, so in the mapping class group, it's a little easier to say you have a subsurface and you have all the subsurfaces nesting inside that. So the stabilizer of that subsurface, its distance is quasi-asymmetrically estimated by the sum over all the things nested inside that. So similarly, if you had this infinite vector and it sort of behaved right with respect to some subsurface and everything nested inside that, then you'd get some kind of partial element, but you wouldn't be able to get a whole element.